Hi everyone, Mr. Companion here. This is lab number 8, Hawaii Hotspot and crustal plate movement. Pretty straightforward lab, quite a bit of math in this, so you're going to want to have a calculator with you. You don't need anything fancy, just a simple 5-function calculator. But that's it. So if we just jump right in, it says here, Introduction. Plate tectonics has been an accepted theory since the 1960s. If you remember, our friend Alfred Wegener was the one that really came up with that. According to this theory, the crust of the Earth is composed of plates that move over the asthenosphere. There are two basic types of plates: heavy, thin, and dense oceanic plates, which are primarily composed of basalt. That's a type of rock. Basically it's a black, high-density rock. If you remember, we spoke about like the inner core and the outer core, mostly made up of iron and nickel. So is basalt. And thick, lighter continental plates. I don't like that word lighter. It really should be lower density, and the density would be 2.7 G/cm3. Whereas the oceanic basalt crust is, again, about 3.0 G/cm3. Do you need to memorize this? Absolutely not. You're going to find that on Earth Science Reference Table, page 10, top right. And here it says that the lighter continental plates, the less dense ones, are composed of silicate rocks, including granite. Movement of the Pacific Plate over the Hawaii Hotspot. The idea behind plate tectonics is that the crustal plates are moving with respect to one another over geologic time. This means many millions of years. The rates of movement of crustal plates can be determined by using data from plate margins along mid-ocean ridges, or at regions known as hotspots. And we found that on ESRT page 5. They list numerous, now about 10. Where the distance and age can be measured. Hawaiian Islands are volcanic islands that are produced as superheated molten material, basically magma, rises upwards from deep within the mantle. As the molten material breaks through the weak places in the crustal plate, a new island will form. And here we have a diagram, albeit not too clear. We've got our volcanoes, and you can see here the magma chambers down there leading from the hotspot. Now you also notice Loihi, which is our new volcanic island. It's not quite an island yet, it's still underwater, is being formed. And you can see here Maui, which is quite a bit older than Mauna Loa. Moana? Yeah, well, that one is relatively new. All right, procedures. Using map 1 on this page and the absolute dates of lava in bold black numbers that represent millions of years before the present. Calculate the age difference between the islands and enter the data on the table on page 3. When there is more than one age on an island, you're going to use an average. All right. So let's take a look. It says here, make distance measurements between the dots of each circle using the scale on the diagram. Convert the distance from kilometers to land or real centimeters, not the centimeters on the map. So we actually have to measure these things. By multiplying the distance in kilometers by 100,000, which is the number of centimeters in 1 kilometer. Hint, it's going to be a big number, and I'm going to show you that. This is, once you see it done, I think it'll make sense. And for Hawaii contains 2 active volcanoes, Mauna Loa and Kilauea. So lava from it is 0 years old, labeled 0.01. The lava on Kauai Island is 5.1 million years old. Thus, according to the hotspot hypothesis, Kauai Island was once an active volcano standing where Hawaii stands today. Okay, so here's our map. We're going to come back to that in a second. If you take a look at your table, though, that you have here, it says here the islands, which in this case would be Hawaii to Maui, you're going to calculate out the distance in kilometers, and you're actually going to figure out the actual distance in land centimeters by multiplying. Then you're going to get the difference in age, in years, and the rate of movement. And the rest is pretty self-explanatory. You have a few questions on the last page. So let's take a look. How old is our first island? If we zoom in a bit, you can see here's Hawaii, the big island. And we've got a few numbers here. So what we're going to do is we're going to take those numbers and we're going to calculate out an average. So from this one right here, we've got 0.004 plus 0.038 plus 0.043 plus 0.15 plus 0.01. And we've got a total of 5 different data points, 1, 2, 3, 4, 5. So we'll be adding these up, and then we'll be multiplying those. All right, so let me just pull out a calculator. Okay, so in this one, it would be 0.43 plus 0.015 plus 0.01 plus 0.004 plus 0.38. Okay, so that gives me a total of 0.839. And then to get the average, we have to divide that out by 5. So dividing it out by 5 gives me, so divide by 5, and that's going to give us a total of 0.1678. Now, what is that number? Each one of these is the age of the rocks found at that location. So each, the average of the rocks' ages on the Big Island of Hawaii is 0.1678 million years old. Million years ago. All right, so on this chart, we're looking actually for the difference in age. Now, in order to calculate out the difference in age, what we're going to need to do is find out the average age for Maui. Now, thankfully, Maui is a little bit easier. Here, in this case, we're looking at 1.3 plus 0.8. And in this case, that would give us what? That would give us 2.1. And then we divide that by the 2 data points that we have, since there's only 2 on this island. So 2.1 divided by 2, that would give us what? 1.05. So the average age is 1.05 million years on that one. Million years ago. So in order to get the difference between these 2 islands, all you have to do is a little bit of subtraction. So in this case, it would be, let's clear out my calculator, it would be 1.05 million years minus 0.1678. Now that I have that, that gives me a difference of, in millions of years, 0.8822. Now, I'm looking for actual years, so I'm going to write a number out. I'm not going to actually say 0.8822. Now, if I know 1 million, looks like this, right? It's got those 3 zeros, and we're looking for 0.88, and you could just basically plug them in. 882,200. So it looks like the difference in age would be 882,200 years. That's the difference between Hawaii and Maui. All right. So once again, I know this is confusing. Let's make sure that we're doing this properly. So we're adding up all the different dates on the island. We're getting a number. We're dividing that number by 5. Why by 5? Because I've got 5 points. That gives me the average age for this island. Adding up these 2, we're getting our average age for Maui. Now that we have our average ages, we're going to take the big one and take away the little one. 1.05 minus 0.1678 gives us 0.882, which is the same thing as 882,200 years. Okay, so our next step is to now find the distance. So it says here, we're going to make distance measurements between the dots of each circle using the scale on the diagram. So here's our scale. And if you take a look, we've got, once again, our 5 points. We've got to go from the middle of all 5, which is about here, right where the A is. And then we've got these 2. We got to basically go from the middle of those. So that would be right there. You're going to grab a scrap piece of paper and you're going to line it up across the 2. You're going to mark off the first one. I'm going to call that one Maui. And I'm going to mark off the second one. I'm going to call that Hawaii. All right, so now that I have this, I could line it up on my scale, and it looks to be a hair short of 100 kilometers. I'm going to call it 100 kilometers. I think that's close enough for what we're doing. So I'm going to go back to my page 3, and our distance would be 100 kilometers. Again, this one's in years. Also says it up here. Now I have to convert to find my land distance. Now, in order to find the land distance, all I have to do is multiply that distance in kilometers by 100,000, right? Because there are 100,000 centimeters in 1 kilometer. It's going to be a massive number. So I'm going to take my 100, I'm going to grab my calculator again so I don't lose any zeros, 100, and I'm going to multiply it by, once again, 100,000. So 100 multiplied by 100,000 gives me 10 million. So there are 10 million centimeters on the actual distance between those 2 islands. It's a lot of centimeters. So, I mean, it's 100 kilometers worth. And then the last thing we got to do is calculate the rate of movement. And this is pretty simple. It's just centimeters per year. So we've got your centimeters, you got your years, and you just have to divide it out. So in this case, it would be 10 million divided by 882,200. And that gives us 11.33 centimeters per year. So you're going to have to do the same thing for Maui to Molokai, Molokai to Oahu, and Oahu to Kauai, I guess. Fun trying to pronounce these Hawaiian words. All right. Okay, so yeah, it says here to calculate out the rate of movement, which we just did. Calculate the average speed of crustal movement, round to the nearest tenth. I went to the 100th. It doesn't matter. Whatever, it's close enough. Yeah, so you could do the math on all these by yourself. I think now that you've seen me do that first one, I think the rest should be pretty easy. Just here, I'd also like to point out we got a pretty cool image, once again showing the magma hotspot, where the current volcano is and where all the previous ones were. And you notice they get smaller, again, because that's with all the erosion, the weathering and erosion that occurs on each of these islands, because they're in the middle of the ocean, and those volcanoes are not growing anymore because they are extinct. They're no longer active. All right, so I hope this was helpful. This is lab number 8. We are just chugging along. Remember, you need 30 in order to sit for the Regents exam. Generally, I do about 40 per year. But that is it. All right, thanks. Bye-bye.